Yes. So today we are going to learn combi games. Uh, okay. So in combi games, so what's the combi games basically? It's like you're going to given some game, and then you most of the times like you have two players, and suppose like we name them A and B generally, Alice and Bob, and then you have like Alice can do some operations, and Bob can do some operation, and most of the time they are same, but sometimes they're different, but they can do some operations on the some given condition and some things, and then you are asked to like prove like who have winning strategy for some value of n's, then what's the winning strategy, and or something like that. And so okay, so let's start. So first of all, like what does it mean by like winning strategy? Because like it's kind of very vague term. So what do you mean by winning strategy? Like suppose you have some game. So game like have some operation, like you given n stones or something like that, and then you do some operation. And suppose like you have finite numbers, like we don't working with infinity. Then after like some amount of choices and decisions, we will end up with like some like game should end basically. So first you start, suppose here, and then you have some choices, you make them the choices, and then after that suppose this is like first player, A makes some choices, then B will have some more choices to make, and so on. And likewise we will like get this kind of decision tree where like you have some given some game. So like suppose like you have like some pile of n stones, and like you can remove any amount of stone, then they're like okay, you can remove n one stone, two stone, or like n stone, and similarly for B and so on. And at the end, because of like either A will win, B will win, or there will be some draw, right? So this is basically like what are like outcomes of game. And if like suppose this is like last term is of like B or someone, and suppose here A win and B win from like this one node, then like what will like B move? Like B will always try to move here, right? Because like this is a B's move. So here also B will move. Like when we have this condition, the game reaches this position, we will always play so that B will win. And like similarly, like suppose they are like A and A, then like we don't have any other choices, and B will always lose, so A will win. And so on, you can like build this tree up. Like, and you can just go up, and like then you can get like, okay, here suppose B wins, but okay, here B win, A win. But now A win and it's A's move, then A will always choose this move, and then A has a winning strategy. Did you guys understand? So like, so
Yes.
yeah. So if game is a finite, then there exists some winning strategy for one player, either winning strategy or draw for one of the player. It's not like always A or B. Uh, so if the games have draw, then we also have a draw position. So uh, let's start with like the simple game. I don't know how many of you seen it. Oh, by the way, like if anyone want like buffer problems, then message me. I have so many buffer problems prepared. But okay, so let's start with the simple game. So game start with like okay, you have two piles of stones. So you have this one pile. I don't know what to call P1, P2. Okay, and this pile have A stones, and this pile have B stones. And for now assume A is less than B. So kind of like suppose this pile have 10 stone and this pile have 13 stone. Then A go first, and he can choose any number of stones from one of the pile and remove them. And whoever can't make a move, like if you don't have any stones in pile, you can't make a move. So whoever can't make a move loses. So whoever wins strategy. Uh,
Sorry, but can you just repeat the question? I was just disconnected for a while.
Yes. So you have two piles of stone, P1, P2. P1 have like 10 stones, P2 have 13 stones. And you can select one like players alternate. So A will go first, then B, and so on. And A will choose one of the piles and he will remove any number of stones he wants from the pile, and they will alternate the moves. And like whoever can't make a move loses. So who will lose the game? Uh,
Okay. Right.
okay. Okay, no one want to go first. That's fine.
Yeah, I think it's
Yes.
will win the game because uh,
Uh, who will win the game?
A the
Okay. So do
start.
you want to explain the strategy? Okay, just tell me what you do for 10 and 13.
What?
Like, can you tell me the strategy? How we play?
Yeah. So I mean, what A will do is A will try to equalize the stones in the sense in the start.
Yeah. So like, if you have 10 and 13, then A will move like three stones from second pile and we get 10 and 10. And then, do you want to explain, Akshay?
Yeah, and then irrespective of what B does, A will just equalize the stones in both the stacks, and that will ensure that A will just win.
Yes. So the strategy is like, okay, this is A played by A. Now, whatever B will play, like suppose B play remove some like X amount of stone from first pile, then A will also play like X amount of stone from second pile, or vice versa. And what we get is like we always end up with like equal, and we know that like our final condition, like the game ends on 0 comma 0, because this is the only condition when we can't make a move. So, and like we always have unequal for B and equal for A, so A will always get the last part of A. So A will end up with this and we can't make a move. So this is like very like intuitive thing to do. Okay, so like the way, like if you ever come up with like piles problem and you tackle, it's like, okay, maybe we will let's try some different game where actually, yeah, where actually you have to think more. Like, so this was like kind of easy, but let's get some more. So we have this problem. Okay, copycat, we will go with that. Okay. So let me explain for you. They are like n stop in the heap, so basically pi. Two player playing the game, they can either remove one or prime number of stone, which divide the like. Suppose currently there are n things, so like we can only choose prime which divide the n, and player who take a last stone wins. So basically, like if A take a last stone, then B can't make a move, so B will lose, or B take a last stone, then A can't move. So for which no matter how. Okay, I will give some time, or like not like solve, but like just give some ideas. So we'll wait if anyone have any idea. Can I just make this chat on? Mhm. Okay, yeah. So basic thing we do in any game question, which is like first thing, because game is very like soft technique theory. Like what you do is like you try to work with small examples, because once you work with like very small example, you automatically get strategy. And basic point is like use the small example and use induction to finish the logic. So let's try with some small example. So suppose n equal to 1, who will win? Two players are assumed like A and B. A will go first. Okay, then so for A, obviously like A will take the last stone, so A wins. For n equal to 2, uh, okay, for n equal to 2, 2 is a prime. So, wait, okay. So,
All
should
try
I do a decline?
explain, right?
Yeah, A will win. So, okay. So, one of the thing is like if n is equal to any prime, then A will always win, right? So, that is what we have. So, for 3 also A will win. For 4, what do you guys think? Uh, So for 4 only, like he can either A, after A's move it can either go to 3 or he can remove 2, so it will go to 2. And like, so now it's thing. So after like A plays the game, B will begin with 3 stones and or either 2 stones. 3 stone or either 2 stone. And like now we can like repeat the same strategy, like because B can remove the prime number, because we can take all of them or this thing. So B will always win for fourth one. Now let's try for 5. Now here's like what do you call like so what's the point of making such a kind of thing? It's like okay, now A has like 5 stones, but now A can just remove 1 stone and there are like 4 stones given to B. But like if you have 4 stone, then B always win. Now you give 4 stone to B to make a first. So A will win. You get it? So basically, like because like A can make a move and go to like B, like the position where B is winning, A will automatically win because that time A is the second player. Suppose for 6 have 2 prime divisor, 2 or 3, or okay, so or 1, like so after first move he can either go to 5, 4 or 3. But if it's go to 4, then again like A have 6 stone, A will remove 2, A will give 4 stone to B, and because of our logic, like second player always win. Like now B is like A. No, like in the question we know like we can remove 1 stone. That's why either 1 or prime P. So that's why A will again win. Now 7. 7 is a prime, so A win. Now 8. Can someone tell for 8 what will happen? So you can't make one move because like after one move, B have 7 stone, but like first player wins, so we'll win. We can't make 2 moves because we will win to 6. Again, they're like B will win. So B wins for it. Uh Now like first of all, like we thought like for primes in work, so like it should be some prime pattern, but it's not coming up to like some prime pattern. It's like first 3 are A, then there's B. First 3 are A, then there's B. So let's like try to work out like quickly. So like for 9 again, like A can just remove 1 stone and A can win. For 10 we can remove 2 stone because 2 divides. For 11, 11 is a prime. For 12, okay, for 12 if you remove 2 you go to 10, that doesn't work. If you remove 3, 9 doesn't work. And okay, those are only primes 12 can divide. So again B. So now like our like, can you guys suspect something here? Like, I mean, obviously, we're getting like 3 A's and 1 B always.
Maybe powers of 4. Sorry,
Uh,
factor multiples of 4. Multiples
yeah,
of.
so our conjecture is like for multiples of 4, B wins and otherwise A wins.
Yeah.
Now, the way we prove this is like, okay, so what are the logic? Like, why this is happening? Yeah, N can't be multiple of 4. So why? Like, so like we know like yeah, okay, let me give you some time to think. Okay.
Can I tell why?
Sure. Like, what's your idea?
So if
Yes.
n is odd, then definitely A will win. We know this because we always subtract an odd number, and when A subtracts something, it becomes an even number. So for it to become 0, it should be A's turn. I mean, after A's turn only, 0 can come.
You mean like even and like wait. You mean like if you have odd number, then you will remove like a always odd number and you will win to even. But like all evens are not win for A or like B. Like see 2, 6, 10 like A wins, but for 4K only the B wins.
I didn't get it. I wanted to say that for making n zero after some moves, A can only do that because B would always give an odd number.
Uh, okay, wait. I don't get it. But okay. So first of all, like, yeah. So first of all, the way we can like go about it, I guess probably it's your idea also, but let me explain in different way. That like, so we will use induction. So we assume like all number less than n, like for all number less than n, this strategy is true. Like A, B works. So and suppose like n is 4k for now. Like same strategy will work for others. So suppose n is 4k and till 1 to 4k we have this pattern, and for 4k plus 1. So for 4k plus 1, A can just remove one stone and A can get 4k. A can give 4k to B, and because B wins if A playing first as a 4k, A will win. So there B wins, so this will win by A. Now 4k plus 2. So for 4k plus 2, we have 2 as a divisor, so we can remove 2 and we can again get to this position. So we can again remove this. Now 4k plus 3. So we want to like if we want A to win this, we want such a odd number, like such a odd number which is like 3, like which is like 3 4k 4l plus 3 times, or prime number, because we can remove prime. We can't remove 1, and so we need some prime such that it's like 4l plus 3 times, so that we can remove 3 and 3, and like it will get again multiple of 4 less than 4k. And because of induction hypothesis, it's win for B, so it will win for A. And can we have like, so like, so A, so this number 3k will have some prime divisor, right? A1, P2, A1, A2, PK, P like R to AR, and like, so two do not divide. So if all of them are like 4k plus 1 type, then you can see like power of 4k plus 1 is like 1 modulo 4, and so like multiplication of 1 modulo 4 are again 1 modulo 4. So that's like, that gives contradiction. So there has to exist some prime which is of type like 4l plus 3, like 3 mod. P is like 3 mod 4 basically. Did you guys get it? Because like the number is like 3k plus 4k plus 3.
It has to have at least one 3 mod
Yes.
4 factor.
Yes, prime. Yes, and
Yeah,
we
prime
can
factor.
take that prime factor, and we can remove it from 4k plus 3 to get some 4 multiple of 4. So A will win. And now why 4k plus 4 won't work is because like to okay, to A to win this one, we need we can't remove 1, and we need some prime factor which will like get us to 4k, but and no prime like divide 4 other than 2. I mean, like, yes, but 2 won't work also. So we don't have any winning strategy for A here. So B will win automatically. And so we prove the induction by A, B is like ultimate pattern. So did you guys get it? So the point to learn from this problem is like we try out base cases, like small cases, and then we try to make conjectures. And out of the conjectures, we do induction basically. Uh, so I hope everyone understanding, right? So now we will begin with like very okay. Okay. By the way, like if I see some people join, so if you guys want like buffer problem, any of you, I can give you some buffer problems. Give me a second. Why it's not working? Yeah. So you can have this buffer from it. These are hard ones, last ones, but yes. Okay. So now we have worked with like base cases or this thing. Now let's think out one more type of like strategies, which is like copycat. So basically, like in combi games, you can't. Okay, so suppose you've given a table, okay, a very nice table, and so you have some kind of coin, like suppose this 1 rupees coin, and you can just place them anywhere around. So the players alternately take moves, and A and B can place coins around this table such that like they won't overlap with each other and they won't stick like this. And like even they can't do this. So like you can place anywhere the coins. And can you tell like who have winning strategy? Like who will win if you
Like
have
we
like
can put anywhere on the table. I
yes,
did not understand.
but table is like finite, some length there. So after some point, like one player can't make a move because like almost everything will be filled. Yes. So yeah. So this is like kind of a known game. So what you do is like you have this table. Now A will place a coin at center. Okay. And now whatever like whenever whatever like direction B will put. Suppose we denote B by this. So if B put here, then A can just like switch like A can take reflection about center and A will place here. So if like now B is supposed to place here, then A can like just place like this. Basically like B will like A will follow the symmetry. And like point is like if B have space to like fill up the gap, then A should also have a space to fill up the gap. And so this is basically like reflection tablet. So you take a reflection of each of the coins around the center and you get another coin to place. And because B can place, sorry, A can place, no, yeah, B can place the coin, A also can place. So A won't lose, and one player has to lose. So that's like B then. So did you guys get it? Like we use like B strategy, like B's thing to copy. We copy the B's idea. Now this is what we call like symmetry or like copycat strategy, where you steal a B's idea. So there is one more very nice problem on this. And like as you can see, like this was kind of geometry problem. Previous was like NT problem. This is kind of again NT problem. So like combi games are like you can mix up like combi and other topics like algorithms and so on with NT also and so on. So they can come up with any type of thing. So we have this nice problem. So we have n and 1 to n minus 1 are written. Now Alice and Bob again take a turn with Alice go first. So if you remove some number k, you have to remove k and all of its divisors. So like if it's like suppose 6, then you remove 1, 2, 3, 6. If some like and suppose like you already remove 2 somehow, like if you play 8 or something first, then you can remove like 1, 2, 3, 6. So 1 also remove, so 3, 6, and so on. And the player who can't make a lose. So okay, why they say so? Okay, anyway. So Alex have winning strategy. Now tell me why. So
One is something which will be removed in every.
yes. So one of the like key observation here is like if you take any number like k, then one always divide k. That's like very key observation. And so you will always remove one. So how can we use this fact? Like anyone like who never seen have any idea? Yes, any idea? Purpose square have odd number divisor. Can you use? Maybe. But think about this like if A had strategy, Alice can remove one. Yes. So okay, can you like formulate? So an idea is intuition, right? So he said like suppose like A don't have winning strategy, so B have winning strategy, and so whatever B plays, Alice can remove one because like both of them going to like on the first move one definitely going to be removed. Either you play like any number or you can play one itself. So point is, uh, suppose Alice play one, and if Alice don't have winning strategy, Bob have a winning strategy by playing K. So like suppose after Alice play one, Bob will play K, and in this K, one automatically get removed. But like we already removed one. So if Bob is winning like this, what Alice and like suppose we follow by other moves, like A will play some other moves and like B will play something for each of these moves. Then what we do, okay, we have this gameplay and Alice will actually move K. And this is like same setup because one is already removed and one also removed at K. And we can follow the same things like if like Bob play now suppose like something like L, then here we will play L and then Bob has to play something L dash to win and we will play L dash only. So if Bob have winning strategy, then A also have winning strategy. And like if Bob doesn't have winning strategy, then A always win. So that's it. A wins. And here like we actually did not find like specific winning strategy. We just copied what Bob did. That's it. We did not put any efforts in finding anything. We just copied Bob.
Why is Alice not having a winning strategy directly imply that Bob has a winning strategy? I mean,
Because this game ends. It can't. So this follows from like first lemma I told, right? So this game ends. So one has to have winning strategy. So okay, because like I know this is kind of confusing at first. So this is wait, what do you call? This is like Zermelo's lemma or theorem, sorry, which is like if there is a finite game and you have like start position and choices by A B, and if you have like come up with this conclusion like A wins, B wins, or draw or something, then you can like build up again back, and then you will get like one of the players has to win here. So one player have winning strategy, or if you like ultimately getting draw, then it will be draw or win for one person. So therefore, like there exists winning strategy for one of them. If A is not winning, then B will win. But A can then just copy everything what B is doing. Otherwise, A just winning. That's it. So everyone follow like how this kind of like copying strategy working. So now we can like start with a very nice problem. We can do geometry now because we done enough NT. So it's time for geometry. Okay. I will give some time for everyone to think. Also, like, tell me if I'm going too slow or too fast or something. I have like lot of questions. Like I start compiling questions and like I just got like some 15 questions or something. I can't break that many, but let's see. Okay. I hope I did not mess up changing names. Yes. So the game is like we have circle and we have endpoints initially. So it's like suppose they are like this. I don't know how many points are these, 7 points. And player can draw triangle using unused and without crossing edge. So like Okay, so if Kenny moves, do this like we can't. Okay, so Dizzy lose here. Okay, that's like very easy steps. Just increase the number of points there. Now here like the if you try to work for small cases, you need like little bit like more cases to work on. So suppose we make this triangle, then like here at most one triangle can make, here at most one, and you can see like here also one triangle can make. So if Kenny moves this, sorry, Dizzy moves this, Kenny will do this, and Dizzy can just move this. So Kenny loses. So this is not optimal triangle. Okay, so let's try. What are the ideas? Like what should we do first?
If n is odd, then
Hmm.
the first player can connect the edge to the two opposite edges to
Okay.
one point to the two opposite points. I meant, sorry, not edges.
Like symmetry, you mean, right?
Yeah, and the other two consecutive points, he can connect that also.
Wait, okay, wait. What do you mean? So these are not odd, right? One, two, three. Okay. Now,
Basically, A would choose any point and connect it to the uh, opposite points. 2 points are there, so two edges.
okay,
Yeah,
like this. Now
yeah,
there
I
are
get.
like fives here and five here. And now what will like
Now, whatever B does on one side, A can copy that on the other side.
yes, exactly. So like once we divide this circle into like two parts, now you can't get any triangle which like cut this triangle. So whatever like this will move here, like player B will do, A will like do the same. Wait, what is this triangle? Weird. Yes. Okay. Yeah. Yes. So this is we can do this for odd because like for odd for each vertex we have this opposite corner of two vertex. So we already have strategy for like n equal to 2k plus 1, which is like we have one vertex, take any vertex, and of diametrically opposite we will have another two, and we make this triangle. Player A will make the triangle, and whatever player B will play in any of the arc, A will just reflect it. And so we will always have reflection. So this is like symmetry, basically. Same strategy, same strats, guys. So, but this is all for odd. What about even? Do we
For
have
the
like
event,
strategy for? Yes.
yeah, we have three opposite points. I mean, there's only one opposite point, but there are two consecutive points to that. So you
Yes.
connect the two consecutive points to
Yes.
the that thing
Yeah.
and you make a triangle. So the same thing.
Yeah. So here we made like triangle and we know like there are no points in this arc. And but what we can do for even is like okay, choose this point. We are dramatically opposite because now we have even number of vertices, but we also have these two consecutive. And now we can just connect them. And like this is also triangle. And if you draw any triangle from using this vertex, it will go out. It will like intersects. So we can't use this vertex. So it will like just vanish, and we can just use the same symmetry strategy. Just reflect everything. So we have been for odd and even, and all integers are either odd or even. So the player B, no, who is this? Player A will always win. So Kenny wins always. So everyone understand this symmetry strategy, right?
Yeah.
So yes, yeah, okay. So we look at the table kind of things like small. We look at the symmetry strategy. Now let's solve very nice problem because like hard kind of problem. Hmm. Hmm. Okay, wait. Take better pinch. This is like very nice problem. I will give time. Okay, I will give time to read and like think about it. Oh, someone annotate. Yes. If you come up with any idea, just speak up or message me. Wait. Oh, you done. I gave the buffer problems. I don't know. Yeah. Yes. The source is nice. Wait, how many of you done this? I hope not many. Oh, interesting. They covered it. Wow, interesting. If many of you seen, then we can take another problem. It's fine. But I currently I don't. Okay. Uh, anyone have any ideas? Please. It's very great problem. By the way. So we have a 6 by 6 table. How to draw 6 by 6 table? It's very terrible table. Right. Yes. So they will choose a rational number and write it in empty square as we will go first. Then all number return each row. The greatest one we color with black. We just color it and then we draw top to bottom. Yeah. Yeah, okay. Wait, don't spoil it or like let people think. So first of all, like this condition, like now we have rational numbers. Uh, so this problem is kind of different. So because we have rational number, we can choose like any small number or any large number, right? Because we don't have any restrictions now. So it's kind of our strategy, what we're going to do. Because Alice can always choose at last like very large number, or Bob can choose like very great.
So the only lines we can make is vertical and diagonal, right?
No, so we can like have like this is large, then this is large, then this is large, then this is large, and then this is large. You know, it says like square can share vertex. So this share the
Okay.
vertex.
Yeah.
We have this line. Uh, is there 2 by 2? So for 2 by 2, it's just work because like one of them going to be like greatest. Let's not think about like okay, it's not obvious why we shouldn't think about 3 by 3. But it's kind of like 6 by 6 is even. But still, if you try for 3 by 3, actually I don't know. Is there I think it's there should be because 3 by 3 is very small. Yes, like suppose we just fill out like this, like B can fill out after 2 moves like the largest number, 3 moves. So suppose we have this largest somehow, and yeah, suppose B move here something. I can work on it. B move here, suppose A do something here, and then we choose this another large number. Wait, no, wait. Yeah, A can choose here, we can do this. A can choose this, but we can still get greater number. If A choose another great number, we can choose here, but it still have Okay, 3 by 3 is very small kids to work. But anyway, so one of the point you can notice from someone asked, like the lines can be vertical or like horizontal, like diagonal. That's not true, but there's something nice fact. Like if you consider any line, like so these are like greatest number. If if this has to be line, the greatest number has to lie here. So what about like if there's no line, like if B is actually winning, so which is like okay, we have these great numbers and then we have other like large numbers here. So all of those lines are like kind of disjoint. And assume like the largest one is in these three by symmetry, then they are like always some kind of this di- disjoint kind of setup, right? And so one of the things is like you do optimization. So first of all, we assume like largest number is in these three because we can just reflect the whole game. So if there's largest number in these three, and if we can't like we have this kind of setup and another large is going here. So there's like always some kind of this division line, something always dividing it. So suppose like it's something like this. Then again there's like something this dividing. You can't connect the like two large numbers. So you can't have like large number here. If A plays here, B has to put like large number here. So what can you think about like it's kind of same as copycat. So the way you deal with this is like you make a peers. So like so B what will B do if A plays here, then B have some like peer connected to it, and if A plays here, B will play here. If A play here, B will play here. A play here, B will play here, and likewise. So he will like connect the two cells always. And so now what he can do? So we can choose infinitely large number or small number, right? So if A plays anything here, X, B will always choose like smaller number, like Y or something. If A play anything here, B will always choose small number. So this guarantees like large number has to lie in these three. Yes, so the motivation is kind of like in so you need like intuition, like okay, if you have two players games, like the kind of one sometimes strategies to make peers, like the copycat basically. Like if A going to play, B going to play like this, and we want to like move out the maximum numbers. It's not in control like what to choose max, right? And where to put, because A will kind of have always a move, but we can choose to like separate out the parts. So like once you pair like this pairs to this to like in this column, suppose you pair this to this, and this to this, and now whatever A play, like if A play here, we will choose a larger number which is not yet written. If A play here, we will choose smaller number, and so this gives like this has to be like large number has to lie here, and you can do like you don't have to make it symmetry, like you can just make like this also. And now like B choose to like make all large number lie here in the row separately. So and one of the thing you can notice, like we have to work some optimization for row, because like it's kind of depend on row, like because we have to connect the rows. So now do you guys find any like good strategy for like this B to not work, like A to not make it? Yes, someone messaged me. The first result. Good. Yes, you're right. Right. So first we choose like suppose like largest number has to lie in these three squares out of first row. And so what you can do, okay, we can choose to like make all largest square numbers lie in these three, and we can make choose like largest number lie in these three, like this. But that still works. Like if largest number is this, suppose, then largest number can be here, and then we can just connect somehow. So can you find something? Like as I told, it does not have to be symmetry. So basically, we don't need this to be here, or like because this is a problem, we don't need this to be here. We can have this like we can connect this two and this two, and we will always force largest number to be this three. And so like, and now like all largest number in like the largest number has to lie in this block and these blocks for each of the rows. So and they can't be connected now anymore. So we always have a strategy. Did you guys got it? What we did is like, so you can like connect the pairs to each like pair of squares and for each row. And so we can make any of the three to be like the largest number has to lie on one of these three square in the row. And then we can choose those three. So we choose such that like they never connected, they never from a connected sheet. Does everyone understand? The motivation is like, first of all, like you have to make pairs. If like it kind of like if B going to win, then B has to make some kind of partitions to like make the all two black line disconnected. And once you make a pairs, you will understand like, okay, we can fix the large number two or three of the six squares. And then it's like about like making the partition. So does everyone understand the problem solution and idea? Okay. Now we can do this problem or this problem. Okay, do you guys want some different kind of, okay. Yes. So see, like for fourth row, what we're going to do is like we connect this square with this square, this with this, and this with this. So if A choose one of this square, we can like put like, so if A choose to put some number X here, like A here, then like we can choose some larger number and put here. If A choose this number square to put, then A can choose smaller number and put here. So like this is largest always than this. This is larger than this is larger than this. And so similar to this. So one of these three square has to large, like has to lie the largest number. Okay. Do you guys want to do some okay, sure. Okay. We will do this problem. This is one of my favorite problems. Okay. Before this, wait, let me explain some strategy. So it's basically what we play doing like freaking, yeah, Russian problem. I have to take this problem. This is like very nice. You can like try some different problems for the first one. So one of the strategy is like we see like for n equal to some value, some set of values, the first player who's going, like suppose A goes first. So if A got these values, A will win. And other like not in n, then B will win. If like there's no draw. Uh, so what do we do? Like suppose we have this. Suppose we fill some numbers first, A2, A3 till something, and now we have some. This is like less than k suppose, and we for k plus one, we will play the moves, and after moves we have like some amount of like k plus 1 minus something, something, this something, 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 something minus. And these all should lie less than k. And like we already define like does that number mean for a or b? If a goes first. So which is like give us like another kind of theory point, which what people like to call like p and n position, which is like suppose like for the p positions are positions where like if a goes first and a given the p position, then a will win. Okay, so all of those numbers are p positions, and n positions are those where like if a goes first on that number, then b will win. And the point is like suppose we have this position, which if it's lead always to the p position, then p is like basically the first player who playing the game. So if it's always lead to p position, then second player will always win. So this is like always n. And if we have some p position which lead to n position, that's supposed to mean like this is a is playing and a play, and now we given b the n position, which is like b will lose. So a wins. So this is like to like we don't always have like first player as A and B, because after one move we switch the players. But P and N position gives like the play if player lands on N, then like second player always win. So if this player land on N, then like this player going to win. So we have this P. And if never land on N, then it will always lose. So it has to be N. Okay. So, and the NP name is like because P for players and N for next player. I actually like I like to call them like red and blue, but let's not do that. Okay. And this is like very great example of NP problems. So not NP problem, NP position problem. Oh. Which is like okay, N stone in table, and then they alternate, and you can remove like p stone where p is a prime, or any or less than n, or any multiple of n. The player who take a last stone wins. So prove Peter has winning strategy. So so like how does that mean? Like suppose like P don't have winning strategy, like Peter don't have winning strategy. So Vasya, I hope that's how we spell it. It's the Russian name. My bad if I spelled wrongly. So like suppose consider some number. We have 90, okay, which is like greater than what? 9 squared. So we can either choose multiple of 9 or prime less than 9. So suppose we remove 18, like multiple of 9. So what we left with? 27. And if Peter don't have winning strategy, then like Vasya always have some number to remove, so that like afterwards this is like P position. So if he's remove like 33, then like after 33, Peter will play and Peter still loses, because we assume Peter don't have winning strategy. But can you guys spot something here? Like we remove 18 from 90, we get 72. Then we again remove 9, we get like the player B remove 9 and we get 63. But yes, yeah, it's odd, yeah. But okay, I will give like if you haven't seen the problem, then like please like talk like what are your ideas, thoughts? Anyone? So so if like P is always losing, then like this N is like it's like N position, right? So after you play this, we get this 27 to B. That means like B is winning. So this is like P position. Yeah, P position. The player who playing. and he gave 33, which is like n position, right? So that like B will win always. But can you see something here? Either not in terms of position also, like in general. So we're removing like multiple of 9 here, like both of them. Then we can just jump from 90 to 33. 33? No, 63. And then like from n position we are jumping to n, which is like not possible. Basically, like if we like just jump directly to 33, we can just play the same game. And if B is winning here, then like A also should be winning. That's true, but wait. Okay, like assume n is not like okay, that's true. If n divides n, then we can take all. So let's assume the case when n does not divide capital N. Like that's not actually like going to helpful in here. So that case can. My point is like from like suppose n, you remove like something like 8, like 9k, like yes, yeah, 9k, and you get some number, and then you going to again like by player B, you're going to remove some another 9l, like multiple of 9. Then we can just directly remove multiple of 9, right? And because like after this play term, we assuming like this is losing for A, then like after this turn B will play, so it should be losing for B also using same strategy. So that implies B won't play the 9. So if you play any multiple of n, like from n, if you remove like something, any like kn, then like B will always remove something like k dash or something, which is like k dash, which is like prime. I hope that's what, yeah, some k dash prime. Did you guys get? So for each of the k and type, like suppose you remove one n numbers, then B will play like p1 prime. If you remove two n numbers, then B will play p2 prime, and so on. And like if you remove multiple of n, then we can just directly remove those, like some of them, and then we get like same position as B. So B will win. So assuming B is winning, then you will choose all this list of primes, and that's now what we do. Actually, what we do. Oh yes. So now what we have here, like suppose this is like how many at most we can choose, n by n, these many numbers, a multiple of 9, n. So the list of prime is like only this much, but because n is larger than n square, this number is larger than n, and we are seeing like number of prime greater than like less than n are like larger than n. That's not true. Like like number of primes less than n is not greater than n or greater than equal to n. So these all primes are not distinct. Some of those primes are equal. So some pi is equal to pj. But let's think about this case. So if you remove some in what is it, whatever stones, then we go from like n to like n minus in, and then we will play a pi, so n minus in minus pi. Now, but the same happening for like j. So if you remove jn, then we're removing minus jn minus pj, but pi is equal to pj. These both are equals. Can we can you see something suspicious from here? Like these are like kind of two same numbers. Like okay, so like so this is I won't reveal it immediately. If anyone have not solved, what you guys can see, like This is also losing for A, and this is also losing for A. And we only differ in like multiple of n. Anyone have an idea? The strategy is like, suppose after this, if we play remove j and stones, so we get pi minus I minus pj minus p. And after this, b will play something like b has to play some prime. Okay. Yes. So the point is like we can actually like jump from like here to here. We can actually remove like j minus I in stones or something like that. Like because these two numbers are different, so we can just remove those amount of numbers. Yeah, this amount of stones if assuming j is greater than I, and if this is losing for A and this is also losing for A, but that doesn't make sense because A will go here and now it's B's turn, so B should be losing. So this implies like two primes can't be same for any n, but we have like n more than n numbers, so that's suppose like two primes has to be same. So we have somewhere winning strategy for it. So okay, let me repeat this thing. So what we can first say is like if you play yeah, so if you have n and if he play like something, he remove an stones, so we get like n minus an, and then if b remove bn stones, so n minus an minus bn, then we can just remove like a plus b stones, and we get like same position as b. So if b has a winning strategy here, then we actually have a winning strategy. So b won't be playing this. So b will play some prime. So for each of the an, b will play some pa prime, right? And we can remove one stone, two n stone till like this, whatever bound. So we have this bound. So that means like we can remove n into n square. So like basically n square stone also. And for that, B always have some prime P1, P2, 3 till like Pn. And so, but now like because like Pn, we have Pn number of primes, like list of Pn number of primes, but like all of these primes are less than n. We know like there are like not many as many primes, so that's why like some of those two has to be equal. So suppose pi is equal to pj, but then like we have this n, we remove n in, then we get this number. If we remove jn, then we get this number, but both of them just differ in like n, like multiple of n. So you can actually jump from here to here. So if this is like A is playing here. So if this is winning for B, A can jump from here to here and get this end position. So A is winning, which contradicts. So which contradicts the fact like they're equal prime, but that's not true. So we get whole contradiction and we A actually have winning strategy. So Peter always have winning strategy. Did you guys understand? And so the bound on this primes, like number of primes is like less than n, is very vague. So the adapted version like some people use is like you can remove k amount of stone, where like k doesn't has to be prime, k just has to be less than n, and this thing still works. We never use the fact dot prime. So like sometimes you're actually not going to use all of the information, which kind of give you the thought process of like processes, where you like you kind of use all information, but they all are not immediately like applicable. We actually kind of disjoin the all information and go with the process. So this was kind of nice problem. I hope you guys like it. Okay, now how many of you have know the do you know the name game? So like name game time. If many of you haven't seen. So name game is basically like you're like A1, A2, 3, AK. So we have piles with A1, A2, and AK stones. And like you can choose A and B are playing. You can choose one pile and you can remove any amount of numbers you want and who have winning strategy. So how many of you actually seen this problem before? Because we can do this one, or we can do some which I'm pretty sure you never, none of you seen because they're from
Can you
secret
repeat the
sources.
question, please?
Okay, the question is like, wait, I will just paste the statement. Assuming I will find it so fast. Yeah. So this is basically me. This is like worst statement anyone ever written. I will explain it better way. You have given several piles. So suppose piles have A1, A2, 3 like AK stones, all are non-zero. And we given two players, we given two players, and they alternate the move. And what they do is like they choose one of the piles and they take like some amount of stone. They can take all of them or some amount which is like less than the pile have. And player who can't make a move loses. So who have winning strategy? You given the set of numbers, like you given the set of piles, and like you have to just by looking at that like tell who have winning strategy. So we played this game at beginning for two numbers. So we have like A and B, if you remember, and like A always win if like A is not equal to B, otherwise B win, which is like copycat strategy. Like if A is equal to B, then like whatever amount A will remove, B will remove same. So they will be 0, 0 at same point. But this game actually get like kind of complicated as you go from 2 to 3 and like 3 to 4. So if okay, I don't think like anyone seen, so I will just start cooking. So I want you guys to like kind of no, they don't have to be distinct. They can be any numbers, and we can like yeah, like they can be any numbers. So we know for like two piles. So what we should do? We should like try to work on three piles, right? So let's do for three piles. So we have ABC. Uh, anyone have any ideas there? That's some basic like claims. So like let's not. So what we like usually do, we go with like small cases. So all of them have one. That's like kind of stupid because like A will remove this, B will remove this, A will remove this. So B loses. So A wins. So what about 1 comma 1 comma 2? Well, again, like A will remove this, B will remove this, A will remove this. A again win. What about 1 comma 1 comma 3? Then we can use same stuff. Like A can actually remove whole pile, right? The third pile. Also, we can assume A is greater than equal to B is greater than equal to C because the all the permutation will be same. So we should arrange them. So this gives like suppose we have 1 comma 1 comma n. then A can actually remove whole pile of n stones. And whatever B will choose, A will choose another one and B can't make a move. So A always win for such a setup. So now, but okay. So now we have 1 comma 2 comma 2. But if you see, like, this is kind of the same strategy because A can remove now this stone and we get this two same. Uh, wait, if I understand correctly, so you said like, oh wait. So all except one stone can't work. So like if you given like suppose 10, 15, 15, and you're saying like A will take all of this, then B can like remove this to one. Then A can also remove this to one. Then B has to play one of this and then A will take this. So this goes into like same as this strategy. Basically, like if we have this setup, like any of the two piles have same number of stones, A can actually take one, like unequal part, and then they can take copycat variation, and so like A will win, and like not uh, like all of them can be equal, and still this works because you just have to take out one and you get copycat variation. So this was not very interesting case. So if we have equal, then like he can just remove one unequal part. So let's try to think about 1, 2, 3. Yeah. Now who should have winning strategy? Mhm. So so like okay, A can't take whole pile because if A take any of the whole pile, there will be two unequal numbers, and that will be like n position because like you give an unequal number to B, so B will remove one of the like unequal part to equal, and he can play copycat variation. So they're not going to take whole pile. So he will either land this one, or he can take like one stone from this, or one stone, two stones from third pile, right? Okay, but if he played this, then this was like in P position, right? So B will win. So A won't play this because A don't want to lose. Uh, all pile, yes, no, like other person will win because now A making move and A giving B some two equal piles. So both of them won't work because like A is like that. Okay, third also don't work. Like A can't, A has to give any of these three, and then we have two equal piles. So we can just remove unequal part and do the same case as we do here. So A is not going to win. This for this tuples B has to win. But now let's think about something more like 1 comma 2 comma 4. Now what? Now there's like one very nice observation, if you guys can notice. So this is end position. Like whoever playing land, whoever player land play first will lose. So
A can remove one from 4.
yes, so A can remove one and A can give B the 1, 2, 3 pair. And now like B is basically A. And we said like B wins for this thing. So basically this is end position. So A will win. And this is like, okay, what about 1 comma 2 comma 5? Like again, like B can remove, no, sorry, A can remove 2 coins and B give B this. So if we have any 1 comma 2 comma n or like K chord such that K is greater than 3, then we can remove like K minus 3 numbers from last pile and give be this tuple in position. So all of them are P positions. Do you guys understand? So assuming we arrange them in increasing order, then so for 1, 2, 3, B wins, and otherwise like for greater numbers. Now let's suppose 1, 3. Now for okay, I hope yeah. For one, we already worked with this case. Who wins here? A wins here automatically. For two, this is same as this position. Like so. Okay, of course we working with increasing order. Why am I bothering with this? For this A wins always. Let's think about this case. 1, 3, 4. So again, wait. Yeah, A can't remove a whole pile because we will give two unequal. Okay, if A remove two from like that position, then we get like we giving B. Wait, something is not good. Yeah, that's true. We're giving B the N position. So A wins. Wait, why am I confused? Yeah, A wins here. Let's think about 1, 3, 5. Wait, I'm confused. This should not be a truth. Am I missing something? Copy. All right. Uh, okay. This is kind of same strategy, right? Yes. So like for any like 1, 3, if any of number is k here, you can just remove k minus 2 stones to get this thing, and A wins here. So now let's think about 1, 4. 4 suppose. Yes. Yeah. I got it. Yeah. Because like we can just permute the tuples. But now this is interesting case. Because like if you remove one, then you giving B the same position from any of these. If you remove two, then you giving the B this position, which this kind of position. Yes. So like if you're going to remove one of them, then we get 1, 3, 4, which is like P position. So A will lose. If you remove two, then we get like 1, 2, 4, which is this kind of like we work with here again. This P position again. So A will again lose. And
Can't
if
we
you
just can't we just remove one from one?
oh sorry. Okay. Not this one. Yeah. So for this A will win because we have two equal numbers. What am I doing? For this position. Yeah, my bad. Okay. We can't remove anything from 5, I'm saying. Because if you remove 1, 2, 3, 4, don't work. If you remove like 1 from here, then we get this position, which is again winning for B. And this position is also winning for B because of these strategies. So B always win. We got another like set of 3 numbers for which B wins. B win for this one and B win for this one. So now from this we can say like for 1, 5 again, like if any number is greater than 5, we can just put it into 1, 5, 4 and work with that. But okay, so what are the like okay, for one like 4, 5 words, for 2, 3 words. So similar strategy we can do 6, 7. If you so see like if you go any lower than this, we can just remove correct amount to get again the P position. And if you do the same here, we again get the P position. So this looks like all 1 comma n plus 1, not n, 2n comma 2n plus 1 words. Works for yeah, I'm not missing. Take 2 from 5. Yeah, then we're going to left with this case, right? We give it this to B, then B will play this, right? Uh, can you see my screen? Actually, can you hear me? Oh yeah, my net is back. Apparently it was gone. But okay, so it kind of seems like this strategy, but that was like too much yap on like first pile playing 1. Let's switch from 1 to 2. Let's try for 2 comma like if they are same numbers, then again we can use same strategy. A wins. So let's try for 2 comma 3 comma 4. So now what do you guys think? If you remove 1 here, we get 1 comma 3 comma 4. But we know like this is n position. Right. Oh yes. Oh, because yeah. Wait. Yeah, this is n position. So A can just play this game. GG. Or A can actually also play this. So A can remove the last one or 3 numbers to get this. And yeah, these are only like A have like 2 n positions to reach. So this is like win for A. Again. Let's try for okay, then like any 1 comma 3 comma. Okay, this is the same because like this is K, just permutation of all the numbers. And we can just play the same game. Interesting. Let's discover. Like we can A can remove K minus 1 numbers here, and we get 2 comma 3 comma 1 to B, and then A win the game. Now suppose 1 comma 4 comma. If you play 5, then he can go to 1 comma 4 comma 5. So that's like covered. So let's try about 6. Yeah. And I hope yeah, this is not covered anywhere. Finally. So after each move, we are not going to like get immediately. Again, you can look up to this. Uh, if you go in like 1 comma 6, then this is like 1 4 pair. So we can remove 3 from here and we get 1 comma 4 comma 3 for B. So B will win. And if you remove any amount of here, like if you make this 3 or 2 or 1, again like B has a winning strategy because like the same strat set here and this thing. Uh, yes, but the point is like if you try like okay, the point is like for game theory, like if you try out like larger cases, like if you're going to try something like this, anything like 12 comma 13 or something 1 comma 3 comma 5 comma 10 or 7 suppose, still like this is going to be like more work to do. And like other than like n equal to 2, like the wait, why annoying okay because we work for 2 and for 3 is like it's not very obvious because okay this works. Now the if you see this does not work, so B wins here. This is n position actually. Whatever you play, B will always have one play to like n position. So B wins for this. B win for 2 comma 5 comma 7 also. And this uh this give like general idea, like it may be something like 2 comma wait, how is this? Yes, 2k 2k plus 2 and 2 comma 2k plus 1 2k plus 2. Yes, And so this give a conjecture that they are basically like adding these two numbers because the same thing happens here with like only specific middle number. Let's you try this case, which is 3 comma 5 comma 6. Have any of you know what are like property of these three numbers being together? Like, oh wait, why? Okay. Try this case. Like, we don't have any symmetry here, and this is actually n position. Like B wins, which is take 5 from 6, then we left with 5 comma 6 comma 1, and so like if this is what A play, B can play like 3 comma 2 comma 1, and this is like losing position. So B wins. Let's see what else you can do. This all looks nice, right? Like this tables looks nice. 2 comma 4 6, 2 comma 5 7. If you try, I guess 2 comma 8 you get 10. 2 comma 9 you get 11. That's true. But for 3, that's like not the pattern. Pattern changes. And pattern is actually very like if you don't like come up immediately with that idea, like it's not very intuitive. It's like very different type of things we're going to use there. So okay, so if you remove like if you make this 5, then this is symmetry again. We giving this to B, so again B will win. For 4, we can remove 2 from here, again win. For 3, same. For 2, we can remove 4 from here, and for 1, we can remove 3 from here, and we can't remove all of them, right? Similarly for this, like you can't make it 4 because that same. We can make 6 1. Okay, let's make it 3 comma 5 comma 2. Then B will make it 3 comma, like I will make it 3 comma 1 comma 2. You lose, guys. Come on, no one. So what do you guys think special about this thing? And like if you guys think like I'm making this so we can play like, okay, anyone volunteer to play, we can play with this thing also. So 3 comma 9 comma 10. Actually this will take time, but it's fine. Will it? Like even this is n position, so like B wins here. So the way we can like try to look up like what are the winning position, losing position, and like not to get confused between like what are like 2 3k and like what is this 1 3k and 1 2k. We define a function. So we define a function from A to B equal to C if like A comma B comma C wins for B, B wins. And so that like if you choose any other number like A comma B comma D, where like D is greater than C, then we can always remove like sufficient amount to get C, and then A will win. So for other this A always win. And for other pairs also, like uh suppose like something K greater than A, B comma D, then again you can just take out to this pair. Sorry, this pair. C. Okay. So we define this kind of function, and where like A is less than equal to B, like okay, we do not, yes. And so we define such a function, and like there may not exist C, but we define such a function, and then we try to see like what we seen till now. Okay, yes. So the point is like, okay, yes, I should define. So for 1 comma 2, this is equal to 3, because 1 comma 2 comma 3 B wins. Then like for 1 like 3 comma 4 doesn't work. 1 comma 4 5. So basically like 1 comma 2n is equal to n plus 1, 2n plus 1. Then again we for like 2 comma 4, we get this is equal to 6. For 2 comma 5, we get this equal to 7. And for 3 comma 6, 5, we get this equal to 6, which is like, so for this like tuples, we get like winning position for B. And like if you choose any other C, then we always get like A wins. And we define like this function because like if you change two parameters, we're getting like different C's, right? So we try to look out like what are the patterns. And like this is like kind of sometimes you have to actually like try out so many cases. Like here, if you like just try to conjecture like, oh, like the PS words are like A comma B and A plus B or something like that, then that actually does not work. Like because like this works. And then like you get stuck. So sometimes you have to try like some more cases than you wanted to. And then sometimes like this time you have to make table like okay 1 2 3 4 5 6 7, then you have 1 2 3 4 5 6 7. So we have this function. So if you have 0, then like all of this number works because you just use symmetry strategy, and this is same here. But now let's see the point. So point is like okay, for 1 comma 2 we have 3, for 2 comma 1 we have 3, like same reflection. 1 comma 3 we have 2, 1 comma 4 we have 5 4 7 6, and same strategy is here. This should be 0, I guess, right? Yeah, everything, the diagonals are 0. Now 2 comma 3 1 again, 2 comma 4 we have 6, 2 comma 7 we have 7, 2 comma 6 we have 4, and for 2 comma 7 we have 5. Okay, till I wrote down everything, I want to like see if anyone like kind of notice the pattern. What is 3 comma 4? Oh, okay, for 3 comma 6 we have this 3 comma 6 5 4. Okay, and now 4 comma 2 2 comma 4 6 7. I hope so. 2 comma 4 7 6. Yes, 4 5 5 4, and I just need to copy this. Yes. Yeah, this should be the table. No, we can't have more than one value because like we define. So if a comma b is equal to c, then like for any other a comma b comma d, we can actually boil it down to a comma b comma c, right? Which d is greater than c. So this function has to give one value. It may not give one value. Sometimes like we don't have such a pair, but for now, if we see there are pairs, and we get this table. So can you notice some pattern in this table? Anything nice? I will just make a border. Interesting border. Just go with it. So basically, like this is like binary. So yeah, diagonals are the same, right? And like 4 boxes, but each box have another 4 boxes again, and each of them kind of have like same symmetry along the diagonal. So, and if you like, so this kind of extend, like if you have like 8 more cells and 8 more here, then this will like just repeat the pattern, right? This and this may not be same, we don't know, but these two are same because they are just reflection. But this kind of dividing into like two, right? And what's the special about two? What is the two? is like it's a binary, like 2 is equivalent to binary. You use binary here. And so what do you mean by using binary? Let's write down 3 6 in binary. 3 is equal to 0, 1, 1, 5 equal to 1, 0, 0. And yeah, this is the one which is working. For like suppose 1, 3, 2, or like 2, 3. Again, this is like this. Or okay, I told you this here. This is very interesting. 1, 9, 10. Again, this is like, I hope I'm not making mistake. 2, 4. Okay, no. Okay, anyone observe something here? All of them. For reference, I will give one more there. 5, 9, 12. This also works. This is, you add 3. When you add 3, 8, 4. Again, does anyone like ring a bell? Like, what are the special about these all triplets? Where B wins? Like, basically the function. Mhm. So point is like there are even numbers of 1 in each of the columns. Like these are like all even numbers of 1, even numbers, and 0 is basically even. Wait, this is wrong. What? Oh, okay, sorry, this is not. My bad, my bad. This has to be 0. Yes. So all of them are even numbers. So if you guys like, you don't have to know, but there's operation called XOR, which is basically like if you have 0, comma XOR 1, then we have 1. 1, comma 1, we gave 0. And for 0, comma 0, we gave 0. Basically, like it's count how many numbers of 1 or 2. And after this XOR operation, if you do XOR operation all of the 3 numbers, we getting 0. And so basically, like if you don't have this, like suppose you have some kind of operation, like basically if you change this to 11, right? And we get like 1, comma 0, comma 1, comma 1. After like there are odd numbers of 1 here. So we can actually make it like even. And you know, like the end of the position is 0, comma 0, comma 0. So all of them are 0. So everything is even. So the name game is like if you have A1, A2, A3 till AK, then if you apply the XOR operation on all of them, and if it comes out to be 0, and if and then only the B wins. Otherwise, yes. And I define XOR here. This is and this is basically like if you convert all of number in binary and you count like each many ones are there, every one column should have like even numbers of ones. And if that does not happen, then A wins, otherwise B wins. XOR, yeah, XOR is basically like gate operation where like if you give it like 0, comma 1 or like 1, comma 0, then you get 1. Then if you give 1, comma 1, we get 0, 0, comma 0, we get 0. And which is like, so applying XOR on like binary is basically like, if you apply this on something like this, which will like basically applying XOR here, and XOR here. And similarly, we apply XOR on all of the list of numbers. So this is ultimate like the name game. So because this is totally different. Like we are working with some pile game where we first use like symmetry strategy, but ultimately the game get that much complicated that we have to use like binary numbers. And now do you guys want to prove this by yourself? How we prove this, or like I want like do you want guys? The operation is defined like this. The XOR is defined like this with this four operations, which is or you can consider like you convert each of the like A1, A2 till AK in binary, and then like you compare each of the columns, and like even numbers of 1 you write 0, and if there's odd number of 1 you write 1, and basically you want like 0 basically. If it's not 0 then A wins, if it's 0 then B wins. I will actually prove. So the way we do it, like suppose all of them are 0, then like A is first move, right? So A will place A has to play something. A will play on one of this column, right? So he will change like one of the ones to 0 and some zeros to 1. So the of them can't be now even number of ones, right? Some of them will change, and this whole operation after one move will get like something after like there won't be even number of ones in each column. Now, what we can do, like we will prove now that if if we have like some XOR, this kind of things, not equal to 0, we can do some move to make it 0. And how it is like assume like for like this columns, right? Assume till this all of them are zeros, like all of them have even numbers of 1, and this does not have even number of 1. So there's we choose like largest number here, okay, out of this all, and with largest number like we remove this thing, and out of this choose largest number. Suppose it's something like this, and now we can remove the sum amount so that this will become 0. So this 1 will goes to 0, and all of here we can just take like complement of that, and like because like we can take numbers we want, we can make this number like, because this is 1, so we can make any number 0 comma something, any whatever we want, and to make this all zeros. So from non-zero we can make it to 0. And so this is the induction, like if we have this and once you make it to 0 then we have smaller numbers, so we can again like play the same strategy. So it's been for if it's 0. So not so okay. So it's actually like it's feel non-intuitive, but the point is like you try so many cases. Like for if you try 3 times, like the way we did it, like actually like you can get it. Like if you try so many small cases like this, and like then it's kind of like this idea. The main idea was like one of nice ideas this, which is like if you have 2 comma 3 words, then anything like 1 comma 2 comma 4 5 won't work, like we can remove 1 and 2 and so on. So for any two numbers we always like we have some unique number, either it exists or not, but it's a unique. So we kind of then try to work with what kind of tuples, what kind of values we have, and like if we get this what this kind of setup, then it's kind of confusing if you don't know what are this like binary like direct intuition. Then you can make this table, and after this table it's kind of obvious like we're working with binary. And once you convert into binary, then like once you convert into binary, it's you can see like all of them have even number of ones. So this is what we call like memes game, the meme game basically, which is like very beautiful. And there's like another like some edited version or something you can call, which is I guess this. Yes, you can try this one. This is like NIM but like harder version or something. And there's another like TST something or some 65 MOH problem, which was again on like NIM game. But okay, so I think I went already 15 minutes over time. But I hope you guys understand like the NIM game, which is basically you try out small cases and you try to make like what are the things works, and like it's kind of like you make a small optimization in every part of the thing or part of the game, and then like you ultimately get the like, last part. This was okay. This was again very nice, like the say N and P position kind of game. This was like strategy. So the game can have copycat. It can have like peers and like so on. So if you want to try, you can try this game, the tic tac toe, which is very nice. Which question? The name game, it does not come as a question. It's kind of come as a theory. The one over. This one, this is hard by the way. Both of them are hard. Uh, Lucien and Malay always play hard games. So anyway, so both of them are hard. This is also kind of hard. This is also fun problem. Like now you have infinite. Like you can use like infinite kind of things, and you can try to work out. This is not that hard, but you have to find strategy like algorithms and set, which is not very easy. And what is this game? Oh, this is like yeah, 2015 C4. Okay, yes. So that's it. Uh, actually, okay. Before we leave, because I wanted to cover this question, but so there are like two more very great questions. But I did not never got time to take this one. But you guys can try this one because I don't know what is like original source. The source I know is from Atul. So you guys can try this one. Anyway, bye. Bye, YouTube. I hope you guys have fun. Okay. Yes, any of you want to say something or anything? Question? Oh, did I stop recording? No.